So in all of, or I would say in the majority of the molecules and Lewis dot structures that we've been drawing and analyzing and looking at, in the majority of those molecules, they have all had just one central atom. And that central atom is really important because that's the one that we focused on to determine VSEPR notation and geometry of a molecule. So the question arises, can we still use this Lewis dot structures and VSEPR in systems that contain larger molecules? Because there are many molecules that have more than one centralized atom. This is another shameless attempt of me sharing some figures from my thesis. So what you see here on the left, that you don't need to memorize, but it is just a stick figure showing the individual bonds of a particular protein, of a particular molecule that I studied for my master's thesis. Its abbreviation is BAX. If you're interested in its structure, I can show you how to find it online. But that molecule, it has over 3,000 atoms, which, I mean, in the protein world is pretty small, but it has 3 over atoms. How would you determine a VSEPR notation for that? There's no one central atom. So the answer to that question is that there are other methods that we use to determine its geometry, but we can use VSEPR in a limited way on larger molecules, like molecules like acetone, a common organic solvent used in fingernail polish remover. We can use VSEPR in a limited way, by saying something about the geometry of that molecule at a particular center. So in this acetone molecule, you see I have 3 carbons, and I'm asking you for the molecular geometry, not of the entire molecule, but using a particular carbon, either C1 or C2, as the center atom. Okay? And so doing that, now we can use VSEPR, at least in a limited way on larger molecules, to say something about the geometry of a molecule at a particular center, as opposed to the geometry of a whole. So in this Lewis dot structure that is drawn for acetone, I can go ahead and determine the VSEPR notation of that molecule at C1 and at C2, and determine the geometry of that molecule at those particular carbons. So for C1, let me get my little pen here. For C1, I know I have my central atom. I have my central atom, A. That carbon, that central atom, is attached to 1, 2, 3 bonded groups. So my VSEPR notation for that central carbon, for that C1, is AX3. And from the chart that I gave you, hopefully, or your flashcards that you're working on memorizing, AX3, that VSEPR notation corresponds to a trigonal planar geometry. Similarly, we can do something similar with C2, with this second carbon. If I wanted to determine the VSEPR notation for that molecule, considering that second carbon as its center, I have that center carbon is attached to 1, 2, 3, 4 bonded groups. No lone pairs of electrons on that C2. So my VSEPR notation is AX4 with a molecular geometry of tetrahedral. So can we use VSEPR on larger molecules? Yes, we can, but in a limited way. We can use VSEPR to say something about the geometry of that molecule at a particular center, at a particular atom of that molecule. One other note to make about molecular geometry with regards to bond angles and lone pairs. Now you'll notice in the chart that I've given you in this chapter, I list the VSEPR notation and the molecular geometries. Those are the ones that you need to memorize. You'll need to use electron geometries for the MindTap homework. But what about the angles that are created in these Lewis dot structures. If you've looked hopefully at the MindTap online homework, you see that there is notation of bond angles associated with these molecules. So MindTap has two figures that list what the corresponding bond angles are for the particular geometries. You do not need to memorize those specific values. You will need to maybe use those for some of the online homework questions, and we will revisit some of this angle concept in chapter 9. But for this chapter, with regards to bond angles with particular molecular geometries, what you need to memorize are these two starred concepts. And really, the first one is the most important, which is that you may have a molecule that has four electron groups, but depending upon what those electron groups are, lone pairs take up more space. And so lone pairs, because they take up more space than bonded groups, they will decrease the bond angle that is present in the bonded groups for that molecule. So you need to know, and that's in general for all molecular geometries. You need to know that, and you should also be familiar with the fact that when you get to have larger structures, if you have lone pairs of electrons, they always want to repel each other. And so they always want to be in places in that geometry where they minimize repulsive forces. So you do not need to memorize specific bond angle values for this chapter. In chapter 9, we'll revisit bond angles for you to use for your online homework. But you do need to memorize these two starred concepts with regards to how lone pairs on the central atom affect the corresponding bond angle in the molecular geometry.